So here's where things start to get a little bit loopy. You can see my pun here, loop. We're looking at magnetic fields due to a coil or a loop of wire. I apologise for my attempt at humour. It's quite late in the evening. So what we're going to look at is the magnetic field due to a single loop first. So here's our single loop of wire, and you can see here that there's a current going round in the clockwise direction. And all you need to do is remember back to the last video where we talked about the right hand grip rule. So grasp that wire with your thumb pointing in the direction of the current, and that will tell you, the fingers will tell you which direction the magnetic field lines are going. So if you grab that wire at any point with your thumb in the direction of the current, your fingers will tell you where the magnetic field is going. And you can see for this first diagram here that if you grab the wire at any point around there, that the magnetic field lines will be going down when they're inside the loop, and they're going up when they're outside of the loop. So rotate your hand all the way around and you'll see that they're going down on the inside and up on the outside. Now all these magnetic fields, it's a vector, and they add together, so the field lines from all the bits around this wire add together when they're on the inside, and they kind of reinforce, and they provide this central vertical magnetic field in the center there, and on the outside you've got them going up. And you can see again then here, if you were looking at it from the top, that you'd have a whole bunch of crosses here which says that the magnetic field is going in the page there, and it's going out of the page around the outside there. And we can see that the direction of the magnetic field inside the loop is opposite to the outside, and you can see there that I've made a mistake, opposite to the outside side of the loop. And of course there's an equation to describe the strength of magnetic field, but this equation is only for the magnetic field inside the loop. So let's define, make sure that we know what all these symbols mean. The large I there is of course the current, and the current is measured in amps. The R here, and for once things make sense, this is the radius of the loop, and that's measured in meters. B of course is our magnetic field at the center of the loop. And you remember what the units of magnetic field are. They are Tesla. And this value here, this value here is, if you recall, the magnetic permeability of free space. So when we're talking about a vacuum in this situation, or close enough to air, and it's something times something by 10 to the minus something, something very small, something by 10 to the minus 7, and you will get that number. It's something like 4 pi by 10 to the minus 7. So, but obviously you won't be able to, well, you probably will remember that now, but it is not something you need to remember. So that is an equation which gives us the magnetic field at the center of a single coil of wire, so a single loop. And you can see that the magnetic field in the center of the loop is proportional to the current. So as the current increases, so does the magnetic field, and it is also inversely proportional to the radius of the loop. So as the radius of that loop gets bigger, so as the bigger the loop, the magnetic field is going to go down, which makes sense because you're kind of getting further away from the wire. Now we're going to wipe all this stuff away and look at what happens when you have multiple loops. So you have what we call a solenoid. Lots and lots of loops joined together. For a solenoid, we have lots and lots of loops of wire all coiled up into one long coil. You can see here multiple turns on this solenoid here, with the current going in and down the page in the front and then popping out the bottom there. This we can show has an effect again of building up the magnetic field within the coils of wire there, and you can see here it's drawn. We have a nice long straight uniform field inside the coil, and it loops around on either end, and that should look really familiar to you. It looks like a bar magnet. It behaves exactly like a bar magnet. Where you have the field lines coming out, this behaves as a north pole. Where you have the field lines going in, it behaves as a south pole. So if indeed you put a bar magnet next to this solenoid or this electromagnet, it will be attracted or repelled depending on its orientation. We can see here that we can determine, and you can do this from first principles. Again, you could take one of the wires, you could, in that coil, you could work out which direction the magnetic field was going. Okay, so you could use your right-hand grip rule. This is another right-hand rule. I'll call it the right-hand solenoid rule. Whereas if you grip the solenoid with your fingers heading down the solenoid in the direction of the current, then your thumb points in the direction of the north end of that electromagnet of that solenoid. But again, you could work that out from just using your right-hand grip rule on individual loops within there. And you can see again that the magnetic field at the centre is related to the current through the wire, measured in amps, the number of turns in the solenoid, which makes sense. The more turns, the more magnetic field is being produced, so it is proportional to the magnetic field. The more turns you have, the larger the magnetic field, and the length of the solenoid. Now it's interesting to note here that the magnetic field strength goes down if the length of the solenoid goes up. They're inversely proportional. I like to think of it more that as the number of turns per unit length of the solenoid goes down, then our magnetic field strength goes down. And that makes sense to me because we kind of, if this number is going down, this number of turns per unit length is going down, it means we don't have as much magnetic field production in, say, 1 centimetre of coil. So the effect is going to be diluted. That's how I like to think of it. So I've just written that here as the magnetic field strength inside will increase if there's an increased density of coils, so the number of coils per unit length. It will also increase if you've got a core of iron in there, so you've got a big block of some ferrous material, ferromagnetic material in there, will affect the magnetic material inside, make all those little bits of that iron core line up, which will just add to the magnetic field. And just reiterating, the magnetic field of the solenoid looks like a bar magnet. So the field lines go out of north and into south, and you can use your right-hand solenoid rule to show which direction that north pole is facing. Okay, that's us for now, and we'll be going through some of these in more detail in class.